example, one side. In this video, we will talk about steps and examples for solving polynomial inequalities. The steps for solving a polynomial inequality are listed here, which I'm not going to go over. Instead, I will show them on examples. You can refer to these steps later on. First example wants us to solve this polynomial inequality. Observe that this is a third-degree polynomial, which is in the factored form, and we want to find the x values that make this polynomial less than. The question is given in the way that the polynomial is on one side and 0 is on the other side. So we skip the first step. The next step is to find the zeros of this polynomial. And since the polynomial is given in the factored form, this step is also easy to complete. So we find the zeros of this polynomial to be -11, 8, and -1. We draw a number line and place the zeros of the polynomial under the number line. And we put zeros to denote that the polynomial has zeros at these points. In the next step, we choose a test value. This can be any real number except the zeros of the polynomial. But we prefer to choose small numbers that will be easy to calculate. For this example, I choose the test value to be x equals 1. And then I evaluate the function at x equals 1. So we find f of 1 by plugging in 1 for x. We get a product 4 times 12 times -7 times 2. And we don't have to find the answer. What we are interested in is just the sign of this function value. In this case, the result will be negative. We first place 1 where it belongs to. It belongs to the interval between -1 and 8. And then we place the sign for the function value above that. This tells us if x is between -1 and 8, the function values will always be negative in this interval. The next step will be to decide the sign of f in the remaining intervals. The polynomial was negative between -1 and 8. And we have a 0 of the function at 8. The factor x minus 8 appears once in the polynomial, therefore it is of multiplicity 1. Whenever we have an odd multiplicity, the graph of the function crosses the x-axis, meaning that the function changes sign. Therefore, in the interval 8 to infinity, the function will always be positive. We repeat this reasoning to find the sign of the polynomial in the remaining intervals. We cross another 0 when we go to the left of -1. Since multiplicity of -1 is odd, the graph will cross the x-axis and sign of the function will be positive in the interval -11 to -1. And we complete by same reasoning. We cross another 0 at x equals -11. Therefore, the sign of the function will change from positive to negative in this interval. The last step is to choose the intervals that satisfy the inequality. We want the polynomial to be less than or equal to 0. So we need to pick the intervals that are signed with a negative sign. In this case, the intervals from -infinity until 11 and the interval from -1 to 8 satisfy this inequality. This is not a strict inequality, therefore the function can be equal to 0. So we can also include the endpoints. So we can include the points that make the function equal to 0. Therefore we include -11, -1, and 8. But we never include -infinity. So the solution set is from -infinity to -11 union -1 to 8. By plotting the function, we confirm that the function is negative, therefore it satisfies the inequality in the intervals we found. I will briefly talk about another example. So we want to solve this inequality. In this case, it is not in the standard form, therefore we need to collect all terms on one side. So we rewrite the inequality. Next, we will find the zeros of f. In this case, the polynomial is not given in the factored form, so we need to use the methods we learned in the previous section for finding the zeros of a polynomial. And by following these steps, we find the zeros of f to be -3 and 1, -3 being of multiplicity 1 and 1 being of multiplicity 2. We place -3 and 1 on the number line and put zeros on top of them. and we choose a test value. This time I choose the test value to be x equals 0, a number easy to calculate. Then we plug 0 into the function and we find f of 0 to be equal to 3, which is positive. So we place 0, our test value, under the number line and the positive sign on top of that to denote the sign of the function in the interval from -3 to 1. Next, we determine the sign of f in the remaining intervals. If we go to the left of -3, we cross a 0 which is of odd multiplicity. Therefore, the function changes sign and it's going to be negative between -infinity until -3. And if we go to the right of 1, the function crosses another 0. However, this 0 is of even multiplicity, therefore the graph doesn't cross but just bounces from the x-axis. So it keeps its sign to be positive. In the last step, we choose the intervals that satisfy the inequality. The inequality requires the function to be positive, so we choose the intervals from -3 to 1 and 1 to infinity. Realize that this is a strict inequality, therefore the function has to be greater than 0, it shouldn't be equal to 0. So we don't include the endpoints and we also don't include the point 1. So the solution set will be from -3 to 1 union 1 to infinity.